Will I be introduced by someone, or I can just
I
start?
will, yeah.
Okay, good.
Yeah. So it's about time for the next talk, but before I introduce the next speaker, we should thank the organizers of the conference. Putting together a conference is always exhausting. I think we all know that it's even more challenging now, and especially trying to juggle everything in this brave new world. I've really enjoyed it, and I've not enjoyed many things on Zoom the past year and a half. So I think that says a lot to the amount of effort that the organizers put in. So maybe we can all unmute briefly and show our appreciation.
Bravo.
And we'd like to thank all the wonderful speakers that really made the session. So thank you.
Well, our next speaker is our last speaker. It's a pleasure to introduce Raquel Perales from UNAM, who is going to tell us about RCD spaces.
Yeah, thank you for the invitation, and let us start. So what I'm going to do first is actually tell you all the results that I'm going to talk about later on. So first, let us remember Bochner theorem that actually was proven in 1946. And he proved that a closed and orientable manifold with non-negative Ricci curvature should have first Betti number less or equal than n. And then the equality is going to hold if this manifold M is actually a flat torus. And after many, many years, Gromov proved in 1981 that actually given a dimension, so here dimension n, there exists a positive number that is small, such that if you have a Riemannian manifold closed, a closed Riemannian manifold that satisfies this condition. So now we are relaxing a little bit the condition of the non-negative Ricci curvature. So here we have this Ricci curvature that is going to be small when multiplied by this diameter square. And actually this quantity to the left is scaling invariant. That's why we do this. So if we have this condition, diameter square times Ricci bounded below by this minus epsilon n, then the manifold that we started with also should have a first Betti number less or equal than the dimension of our manifold. And Gallot, after 2 years of the proof given by Gromov, gave a very different proof. And Gromov conjectured what would happen for the case B1 of M equal to N. And one of the first results answering the conjecture of Gromov was this result by Yamaguchi. So what Yamaguchi proved was the following thing. He fixed some constant that is going to bound the diameter of our manifold and fixed some dimension k. So this dimension k is less or equal than the dimension of the manifolds that we are going to look at. And given these 3 parameters, there exists a small epsilon that depends on the dimension of our manifold, the diameter bound, and this other dimension bound, such that any manifold of dimension n closed that satisfies this set of conditions is going to be a finite, then a finite cover of M fibers over a K torus. Okay, so then here you can take K equal to N, and then you will see that M is going to be a torus. So then after many, many years, Colding came, and in 1997, he proved Gromov's conjecture. So he proved that if you fixed a manifold, well, if you fixed the dimension, sorry, then actually, okay, sorry, I'm reading in a different order. So he proved Gromov's conjecture. So this is Gromov's conjecture. So once that you fix a dimension n, you can find a small epsilon such that any manifold that is closed of the dimension that you have fixed and that satisfies this bound in the diameter squared times the Ricci curvature, so bounded by this minus epsilon n, and whose first Betti number equals the dimension of the manifold, has to be homeomorphic to a torus. If n is different than 3, and homotopically equivalent to a torus if n equals to 3. Okay, so this kind of proves the conjecture of Gromov about getting torus when the first Betti number equals n, and we relax the condition on the Ricci curvature bound. But later on, Cheeger and Colding upgraded this result, and instead of showing only homeomorphic and homotopically equivalent, they show that you can actually get a bi-Hölder map. So you are actually bi-Hölder to a torus. And now let me read this first theorem that I wrote here. This first theorem, it's used to prove Colding's second theorem here. And it just tells you that if you have a fixed manifold, then there exists some epsilon that depends on this fixed manifold, such that any other manifold that has some Ricci bound, Ricci lower bound. I mean, this minus n minus 1 doesn't matter really much. You just want this to have your manifold with a Ricci lower bound. But so the important thing is that if this n manifold is close to the original manifold, and close means with respect to the Gromov-Hausdorff distance, and how close is given by this epsilon that depends on your manifold, then actually M and N are homotopically equivalent or homeomorphic as the conclusion of this theorem. Okay, so actually this first result is used to prove this second result, which is the conjecture by Gromov. Okay, so far so good. And now what would I like to talk today? So with Andrea Mondino and Ilaria Mondello, we generalized the previous results. So the result of Gromov and Gallot, and also the result of Colding, and actually the result of Cheeger-Colding. So what we are going to do is we now work in a class of spaces that are called RCD star Kn spaces. And we show that if the diameter of our space multiplied by this k, and now this k acts as the lower bound of our metric space. So this is a lower bound. Okay, so let's start again. RCD is a synthetic notion of a manifold with a Ricci lower bound by kappa and dimension bounded above by this n. So what we are saying is that, again, if we have this lower bound that only depends on the dimension of the diameter of our space square multiplied by the Ricci curvature bound, then we will get again that the Betti number, the first Betti number, is bounded by this floor of n. So one more thing that I have to say. So here the dimension n is actually a real number between 1 and infinity, and that's why we have to put a floor here. And we also have to define what it means first Betti number for this class of spaces. And in this case, we are actually going to call it revised first Betti number, because the fundamental group for these spaces is called revised fundamental group. So this is the first part, and the second part is actually the bi-Hölder homeomorphism that Cheeger and Colding proved, but for this class of spaces. So actually, I mean, this bi-Hölder homeomorphism to an n-dimensional flat torus, we have to break it into 3 different statements because we are dealing with the spaces that are non-smooth. Yeah, and that's why we have to break this into 3 pieces. So as I told you, this n that we started with might not be a natural number, an integer. But in this third statement, if your n that bounds your dimension is actually an integer, then what we are going to get is that the m, so here m is a measure on our metric space. It's actually going to be the Hausdorff measure of dimension n multiplied by some positive number. And then our space is going to be bi-Hölder homeomorphic to an n-dimensional flat torus. Okay, so far I haven't said what is an RCD space. What you have to believe me is that RCD spaces, as I told you, are generalizations of Riemannian manifolds with a Ricci lower bound and a dimension upper bound. And they also include Alexandrov spaces that Jesus described in his talk. And also they include quotients of manifolds that have Ricci lower bounds by groups acting on them, by groups of isometries acting on them. Okay, so what I'm going to do is just a brief idea about how to prove the theorems that I just showed you. And the easiest case is to start with the proofs in the smooth setting. And they go as follows. So these are the people that we are going to deal with. So we have a closed Riemannian manifold. Then we will consider the universal cover space of M. Then what we are going to have is the commutator of the fundamental group. And we are going to mod out the universal cover space by the commutator, and then we will get a covering of our original manifold, so a covering of M. And then what we are going to do is we are going to mod out our universal cover, our fundamental group by our commutator. And we are going to get this group gamma. And this group gamma is actually going to act in this M bar by isometries. And here I put this in red because actually this part, we really don't know if this is true for the class of RCD spaces. But for Riemannian manifolds, we know all this line is true. Okay, and good so far. And then what we are going to do is I'm going to define another subgroups or another groups. And so this is going to be a subgroup of this gamma. And here I put a 3. The 3 is meaningful later, and they are going to be isomorphic to Z to the power P1M. And then we are going to take a quotient of M bar with respect to this new subgroup. And we are going to get a new manifold M prime. So these are our participants. And now let's see how we prove Gromov and Gallot result about how to bound the first Betti number of our manifold. And the first ingredient to prove this is a lemma by Gromov that tells you that in your manifold M bar, if you fix a point, so you fix a point X bar, and you can choose some K, an integer K, that is going to be, well, greater or equal than 1 because it's an integer. Okay, so given this information, what we can do is find a group, gamma, that is going to depend on this K that we fixed here. And the thing is that this group is going to do the following thing. So the point that you fixed, you can move it by elements of gamma, so of this gamma that was actually the quotient of our fundamental group and the commutator. So, okay, so this subgroup gamma k consists of those elements that to your fixed point, you move it with one gamma, and you move it and it's going to go far away. And how far away? Well, it's going to be given by this k times the diameter of M. So basically, your elements of your group won't collapse and they will move a certain distance. And also, the other thing is that, okay, they will move far away from bar X, certain distance, but they don't move too far. So we also have this other bound. So they move at most 2 times k, the diameter of M. And well, I'm going to skip the sketch of the proof, but it's basically, I mean, this gamma is an abelian group, so you can think of it as a set having, I mean, then you have linearly independent elements, and you want the ones that have maximal J length. And this J length has to do with satisfying this inequality, okay? And once that you make your elements to satisfy this identity, then they will satisfy this identity, okay? So that was our lemma in order to prove the bound on the first Betti number of our manifold. So we actually want to find this, this epsilon that only depends on the dimension of our manifold. Okay, so what we are going to do in order to prove this theorem is the following. So without loss of generality, we can assume that Ricci of our manifold is going to be negative. We won't use it, Ricci non-negative here, but we will use it later because we are going to use Bishop-Gromov volume comparison. Okay, so once that we decided that Ricci is less or equal than 0, we apply the previous lemma, and I will choose k equal to 1. So once that we choose the previous lemma, well, we have this subgroup, and we know how this subgroup moves a fixed point. So it moves it between diameter of M and 2 times diameter of M. So actually, I can look at balls around this point X, and actually I'm going to choose this big radius. So it's going to be 2 times r diameter of M plus diameter of M over 2. And this r is just a positive number, okay? So we can consider this ball, and this ball, what we are going to do is we are going to put smaller balls in this ball. So imagine that you have a pizza, a pepperoni pizza, and you are putting pepperonis in the pizza. And these pepperonis are given by these smaller balls. And because we have these bounds, actually these pepperoni balls that we are putting in our pizza are disjoint, and we know how to count them. So actually we have, so this amount of balls, this is how we count the number of balls that we can put in that are disjoint, and they are all going to have the same amount of volume because this gamma is acting by, I mean, it preserves measures and also it preserves the distance. And obviously, because we are filling in our pizza, well, the volume of this pizza is bounded by this quantity. Okay, and one thing that then we note is that this number of mutually disjoint balls that we can put, it's bounded by B1. So B1 is less or equal than this quantity of disjoint balls, and also the number of disjoint balls that we can put is equal to some polynomial thing that depends on R. So So look at this. So we have a polynomial thing, but then we will use Bishop-Gromov. And Bishop-Gromov for Ricci less or equal than 0 is actually hyperbolic, some expression that has to do with hyperbolic sign. So polynomial and hyperbolic sign are going to give us a contradiction. And that's how we will get that our first Betti number has to be less or equal than n. And another thing that this theorem gives us is, is basically this thing, that if we have a fixed diameter on our manifold, our original manifold M, then when we pass to this manifold M bar, and we look at a ball around the fixed point with some certain radius, we will know how many balls I can fill in, like mutually disjoint balls that I can fill in this bigger ball. And this is important for what happens next. Okay, so this proves Gromov and Gallot. And now let us see how Colding proved his theorem about obtaining a torus. So the thing is that what we are going to do is the following. We are going to have a manifold that is going to satisfy some Ricci bound that is going to be very close to 0, but it's going to be negative. So our manifolds are going to have Ricci lower bound by minus delta and first Betti number equal to the dimension n, and we are going to fix the diameter. Okay, and once that we do this, or if we have these conditions, we can actually prove that in our manifold M tilde, remember that M tilde is the quotient, it's a covering of our original manifold, then the balls in M tilde of certain radius, and this radius is actually very big. So it's this epsilon to the -1. It's going to be closed in Gromov-Hausdorff sense to balls in Euclidean space. And how close? Well, how close is going to be given by this epsilon that we can choose. Okay, so in this theorem, in order to prove this theorem, what one has to do, if one follows Colding's original proof, he has to use something that looks like harmonic coordinates. But in our new proof of this theorem for RCD spaces, we don't use these harmonic coordinates. We will use a different tool. And basically, this is one of the few things or few parts in which our theorem is different to the proof of Colding. Okay, but once that we know that, that if Ricci is small enough, our balls in M bar are almost Euclidean, in order to prove a Colding result, what we can do is, well, now we take a sequence of closed Riemannian manifolds whose Ricci is small, and actually we want the Ricci to go to 0, so it's negative, but it will go to 0, and we want the first Betti number equal to n, and the diameter to be fixed equal to 1. Okay, so we have this sequence of manifolds, and what we are going to do is fix points in our MI bars, and now I'm going to choose this subgroup that has k equal to 3. And once that I choose this subgroup, we already have seen that this was a participant in our story. So we take this quotient of MI bar by this subgroup. So we get another covering of our original manifolds of MIs. And these MI primes are the ones that are going to be isometric to an n-dimensional flat torus. Okay, so how does one prove this result? So basically what one has to do is prove equivariant Gromov-Hausdorff convergence. So what one has to do is to show that these MI bars converge to Euclidean space. And actually they converge to Euclidean space because of this theorem. So this epsilon -1 is going to go to 0 because this minus delta, which in our case is minus ki, is going to go to 0. So we will get these mi bars converging to Euclidean space. And then these gamma I3s are basically, I mean, they are isomorphic to Z to the power n. So we are going to be quotient out by this space, and we are going to get a torus. Okay, and this is a proof in the smooth setting, and I'm just going to run out to show you how to do the non-smooth setting. And first, in the non-smooth setting, I told you that there is no, well, the notion of fundamental group is basically replaced by something that is called revised fundamental group. And that is because there is no such thing as universal cover space as we know it as for Riemannian spaces. So actually in this class of spaces, these RCD spaces, a universal cover space for some metric space is just going to be a connected covering. So it doesn't have to satisfy semi-locally simply connected. It just has to be connected and to satisfy a universal commutative triangle. Okay, so commutative triangle. And once that we have this space, so we call it universal cover space. And what we can really define with this covering space is the group of deck transformations. And this group of deck transformations is what we call the revised fundamental group. Okay, and then a crucial point for our theorems is that Mondino and Wei show that if you start with an RCD space, then this RCD space will admit a universal cover space, and the universal cover space is also going to satisfy the same curvature and dimension conditions that we started with. And then with Mondello and Mondino, what we show is that this revised fundamental group is finitely generated if our space that we started with is compact. And because then this is finally generated, we can define a revised fundamental group, which is just basically, we have the revised fundamental group, we mod out by the commutator. And so then this can be written as, I mean, it's going to be isomorphic to the torsion part plus the non-torsion part. And you can define your first revised fundamental group as the rank of this thing. And it's going to be well defined because of this result here. And now another thing that we had to do is we have to make sure that quotients of RCD spaces are again RCD spaces with the same curvature and dimension conditions. And for this, there were other results actually proven by Galaz Garcia, Kel Mondino, and Sosa, but they didn't apply to what we wanted to do. Okay, so now with this in hand, proving that the first Betti number or the revised first Betti number is bounded below by this n, that is identical as the proof given by Gromov and Gallot. And the only thing that I told you that is different is how, so it's basically the replacement of this theorem of Colding. And so for that, we have to do, instead of using harmonic coordinates to show this Gromov-Hausdorff closeness, what we have to do is a splitting type argument. And my time is almost over, but you can split lines. So actually one splits lines and splits lines, and one can get some result that is very, I mean, that actually looks like Colding's result. So here we are saying that a ball in our space is very close in Gromov-Hausdorff sense to a ball in Euclidean space. I mean, here it's Rk times y, but if you keep splitting, you are going to get n elements, and this y is going to become a point. Okay, so this is an induction argument, so that's why Rk is going to be replaced by Rn, and then almost everything follows through. And I guess that's it.
Are there any questions for the speaker? Just a comment, I do like your last graphic. I think that's great, given the content.
I mean, the last line is, I think I'm the last speaker of the MCA, like not just of the session.
Oh, that's very
Yes,
fitting.
you are the last one.
Well, Ramiro.
No, I just wanted to say, so it's a bit hectic at home, but hopefully I can say a few words. So yeah, I wanted to thank Raquel and all the speakers for their wonderful talks. And I guess we should also, since we are being recorded, we should thank the organizer of the conference. And I guess in particular, I wanted to thank Gaston Garcia from the virtual committee, because yeah, he was very nice to reply to our 1,000 emails through all these months. And all, to all the participants as well. I hope you enjoyed the talks as much as I have, and I hope we see each other in person, you know, hopefully not in the too distant future. So yes.